Picking up from where we left off in tutorial 5, I want to run our first simulation. We have the same configuration here as in part 5, and what we're going to do is we're going to simulate for an axial optical fiber the increasing fill fraction of nanoparticles. We're going to measure the reflectance and other optical properties from the fiber when the fill fraction is 0 up to some dense value. In the main panel, you can get a summary of the simulations already in PAME. So if you wanted to do multiple simulations at once, you can just add entries to this table. But we only need to do one. So we'll call this fill frac. We'll do 10 increments. So come over to the simulation tab, and now we have to specify the parameter that we're simulating over. Some of the most common simulation parameters are already here for you. So for example, layer thickness would simulate a layer getting wider and wider, maybe to simulate a film being vapor deposited on a surface and the thickness of that film grows. Another common one is the nanoparticle shell thickness. So if you wanted to simulate a growing nanoparticle shell as proteins bind, this would be a shortcut. But the one we want to look at is layer fill fraction. Layer fill fraction corresponds to the density of the nanoparticle film in the stack. Recall that the stack is 24 nanometers thick and it's occupied by uncoated gold nanoparticles in water. In principle, any numerical parameter can be simulated. Any parameter that you can come out here in the menu and fudge with, either through a toolbar or through a widget, can be set in the simulation. There's a tree viewer that you could use to browse the available materials. The only problem right now is that this is incomplete and it's not rendering very nicely because I'm using the Qt backend. And the WX backend, this would render really nicely. So let's content ourselves to simulate the layer fill fraction. Again, we can do this in 10 steps. We could add any notes that we want. So we'll say this is a simulation of nanoparticle density increasing on axial fiber. Choose your output directory. I'll save it to my desktop. And for the extension, let's save this as a pickle. Right now, the JSON extension is not 100% supported, and in the future, though, everything should be migrated to JSON. The storage tab lets you pick how you're going to save the data. So how much information do we want to get out of the simulation? For example, I've been only looking at the reflectance, transmittance, and absorbance, but there are several optical properties stored or that can be computed every single time I update these. For example, our delta and our psi are the ellipsometric amplitude and phase if you're doing ellipsometry. We're only going to really worry about R, T, and A, so I'm not going to select any of these other ones. This box is useful if you want to save the whole state of the program for every step in the simulation. That's going to save a lot of data, but it's useful if you plan to come back and do exploratory analysis, because in saving this, all the information in the simulation, it will be accessible to you in the analysis. Here we specify, do we want to look at the average of multiple angles or not? So for example, the spread here was due to the fact that we had angles ranging from 0 to 16 degrees. But if we had averaged them, we would just be looking at one curve. Here we can also make that, we could specify, do we want to save the average only, or the full spread of angles, or do we want to save both? Let's content ourselves with average. The multi-layer stack lets you pick which properties from this plot you might want to look at in post-processing. For example, we consistently look at the permittivity of the layer, but we also look at the optical cross-section of the nanoparticles. In certain simulations, for example, simulating the nanoparticle shell filling up with proteins, this changes through the course of the increments of the simulation. So here I could specify specifically that I want to save some of these. They're all accessible. These attributes are all accessible otherwise, but they're easier to access if you specify ahead of time which you want to store. Furthermore, are we only interested in the selected layer in the stack or all the layers? When I do the simulation, am I only going to be looking at parameters, analyzing parameters from this layer, or are there any interesting parameters in these layers that might change through the course of the simulation? For our simulation, we're leaving the substrate and the solvent unchanged, so I'm only going to select the selected layer. And there's a lot more here that should be explained in a later tutorial. We see that this layer fill fraction actually corresponds to a variable called selected material.vfrac. I also could have called this material1.vfrac to specify its position in the stack, although it's counting from 0, and unfortunately this label is counting from 1. But in any case, let's run the simulation. Oh, nope, I'm wrong. It is counting from 1. Thank you. So material2.volume fraction, that works. Maybe it doesn't work. Okay, I guess we should just stick with the shortcut. That's why these shortcuts are in here. Selected material.vfrac. Oh, what are the ranges? Well, we're going to start from 0. And we're going to go to a volume fraction up to about 0.2. 0.2, by the way, is, if we set this to 0.0.2, it's a disk coverage of 38%. This volume slider here is what we're simulating over here. So I'll go ahead and start that simulation. And in the terminal where I have PAME loaded, you should see that that's going to run 10 iterations. When this is finished, it's going to save to a file, and this is going to freeze me out until the simulation is done. But it's going to save a pickle file to the directory that we specified already, and I can analyze that later in an IPython notebook. So simulation complete, yes, I would like to save, and it tells me it was saved to a file fillfrac.mpickle, and we'll look at that in an IPython notebook in the next tutorial.